Ladies and gentlemen, welcome back. In this video, I'm going to derive our earlier result, which was the expression, or rather the parameter that measures the gravitational redshift in Schwarzschild spacetime, and we're going to derive that same result in a more general spacetime, although that spacetime is not going to be entirely arbitrary. Rather, under certain condition, or a spacetime with certain characteristic will going to show us the same result, which is consistent with the result we have just derived earlier. Specifically, in the Schwarzschild spacetime. So, in a more general spacetime, we're going to have a consistent and similar result if our spacetime is going to have the following characteristic. So what I'm assuming here, so this is basically our list of assumptions. The first assumption is that the metric we're going to deal with, or the metric that is going to encode all the information of the spacetime, is going to be stationary. Now, what does it mean for a metric to be stationary? It means the metric components are going to be independent of the time coordinate. So let the time coordinate be x0, and if we differentiate, or rather take the partial derivative of the metric coefficients with respect to that coordinate, we're going to have 0. So this is the definition of being a stationary metric. On top of that, we're going to have another condition, right? This condition tells us that there will be no cross term between the spatial indices and the temporal indices. So that means that I am not going to have a 0 term here and then an I index here. So 0 stands for the first index, which is the temporal index, and I can take the value 1 or 2 or 3, which are the placeholders for the spatial indices. So we know already that the metric components are not function of the time components. In general, they can be functions of all the spatial components, so that's why I'm going to write a 3 vector as the argument of the metric components. And there is no cross term between the temporal part and the spatial indices, so this is going to be 0. Alright? So once we do have that, then our metric tensor should look like this. So the line element equals g0, 0, which is a function of the spatial coordinates, and that's why I'm going to write a 3 vector, and then dt squared, plus gij, both spatial indices, remember the condition in number 2, is also a function of the spatial indices, and then I have dxi, dxj. If we want to express that in a more mathematically appropriate notation, then of course we're going to impose the tensor notations and the tensor products. So in that case, ds squared is a geometric object, so I'm going to underline that. D is an operator here, right, which is acting on this coordinate t, and this is creating a 1 form, and the metric tensor is a symmetric object, so this is going to be dt, tensor product with dt, whereas in here we have dxi, dxj with tensor product in between. So we can see, even though this geometric object has been expressed with the help of coordinates, the whole object in its totality is a coordinate-free object because this is a geometric expression. That's just a little bit of technicality that we have followed. You don't have to go through this because the real physics is in understanding what is in each of those things that we have just written down. And I think at this stage, if you're watching this video, you should understand most of it. If you're not familiar with GR, then of course you need to be more familiarized with these topics from the very beginning. And if you are a subscriber on this channel, you know I make GR contents along with other branches of physics. So hopefully by surfing the contents in this channel, you will be able to get the relevant introduction someday. Anywho, that's a bit of self-promotion right there. Let me get into the discussion that was ongoing before I digressed. So, assuming that our metric tensor fulfills these two conditions, then it should look something like this. Then this allows us to figure out the gravitational redshift in this spacetime, which is expressed by a parameter called the redshift parameter. It's been written by a lowercase z or z, depending on where you live and how you pronounce it. I'm going to go with z here. Z is going to be equal to square root of a certain ratio, and the ratio is this: G00 at the position of the emitter of the signal divided by the 0 component of the metric tensor at the position of the receiver minus 1. So this is going to be the result that we are going to derive now, and hopefully with a bit of luck you will be able to see the underlying beauty of general relativity from this discussion. So let's go on with it. So now let's try to draw a diagram that represents the situation we are describing. And like elsewhere in physics, if we can draw a picture good enough, that helps us to envisage the underlying physical problem properly, then half of that problem is solved right there. So that's exactly our goal in here. So what we do have here are two word lines. This word line represents that of the emitter, and this word line represents that of the receiver. And of course, at this point, the emitter releases a photon signal. So at this point, the full velocity of the emitter is going to be a tangent to the word line. And similarly, at the point of receiving, its tangent is going to be the representative full velocity of the receiver. The momentum of photon, right, is going to be also a tangent to its path, and similarly the momentum of the photon is going to be a tangent to its path at this point as well. So let's just call this point A and this point here to be B, and the full velocity of the emitter is written by U sub E, and to emphasize the fact that this is the velocity at the point A, we'll also put A in the argument. In a similar manner, we write the full velocity of the receiver by this notation as a full vector, U sub R, and similarly, to remind us of its locality, we write the argument B. The momentum of the photon is written as P of A, and the momentum of the photon here is written as P of B. Now we need to establish a coordinate system. So this word line is written in the coordinate x mu of E, and of course this coordinate is parameterized by the proper time measured by the emitter, and Similarly, in here, let x mu r represent the word line of the receiver, which is parameterized by the receiver's proper time tau r. And that more or less completes our picture. Now the rest is very easy. We are going to follow a systematic rule. So what we are going to do is to find out the energy of the photons as observed by the emitter at this point A and the receiver at this point B, and from the relationship between the energy and the frequency of a photon, we are going to figure out the relationship between the frequencies as well. So our first job is to figure out the energy of the photon. Now, the energy is not a geometric quantity. It's rather dependent on the coordinate and specifically on the observer as well. So the energy of the photon as observed by A is given by this. E of A equals the momentum of photon at that point dotted with the velocity of the observer at that point as well. And this is going to give us simply P mu at A and then U E mu as A. Similarly, B is going to observe the energy of the photon at point B to be the dot product between the momentum of the photon at point B dotted with the full velocity of the receiver at point B, which in turn is going to give us P mu at B and then U R mu at B. Now, if we do take the ratio between these quantities, we automatically get the ratio between the frequencies as well. So we have E, the energy measured by the receiver, divided by the energy measured by the emitter, is going to be the same ratio of the frequency measured by the receiver and the frequency of the photon measured by the emitter. And if we substitute the quantities we have derived just earlier, then we have this result right here, where in the numerator we have momentum at point B dotted with the full velocity of the receiver at point B divided by the momentum of the photon at point A dotted with the full velocity of the emitter at point A. Now, if these two quantities are going to differ, this ratio is not going to be 1, and the deviation from 1 is going to tell us that a redshift has occurred. Now, the momentum of the photon is constrained by this equation right here. The dot product of the momentum with itself is going to be 0 for photon and non-zero for massive particles. Since we are talking about photon, this is going to be 0 naturally, but the calculation simplifies greatly when we consider both the emitter and the receiver to be fixed in their position. So that means the spatial component of the velocity of the emitter, so I denotes the spatial coordinate, whatever coordinate system you want to choose. In this case, it's going to take the value 1, 2, 3. This is by definition the spatial velocity, so we have the derivative of the ith component of the position with respect to the proper time, and this is going to be 0. The same goes for the special components of the full velocity of the receiver, and this is going to be 0 as well. So in both of their cases, we have, since both of them are assumed to be massive, the constraint between the components of the full velocity is given by a relationship which looks like this. This is going to be c squared. And since the special velocity is 0, so we have g 0, 0, u0, u0 is going to be c squared, and u0 is going to be c divided by square root of g 0, 0. Now, since we have this contraction right here, mu contracted with this mu here, and the same goes for these two indices here as well. I should have used different indices here, of course. It should be nu and nu. But nevertheless, there is a contraction in both the numerator and the denominator, and the fact that the special components of the full velocity is 0, this finally gives us a much more simplified result, which is p0 at b divided by p0 at a times, instead of this components of the full velocity, we can now substitute this result right here, which is going to give us the ratio within the square root d00 at a divided by d00 at b, which are the metric components, the 0, 0 metric components at the corresponding points. Now, it is at this stage where we are going to implement the stationary condition, which basically says the components of the metric tensor are devoid of the time coordinate. So that means if you differentiate with respect to the time component, or rather the time coordinate, we are going to have 0. And this has an interesting consequence, because from Lagrangian mechanics we know that if the Lagrangian is devoid of a certain coordinate, then the corresponding momentum is going to be conserved. In this case, the Lagrangian is written as g mu nu x dot mu x dot nu, and this is applicable for both null geodesic and for massive geodesic. And indeed, the same result stands here as well. So since these guys are devoid of the time coordinate, then the corresponding component of the momentum, specifically the 0th component of the momentum in this case, is going to be constant. What an interesting result. So finally, we have 1 plus z, and this is going to be nu r divided by nu e, and this is going to be the square root of the ratio of the 0, 0th components of the metric tensor at the releasing point and the receiving point of the photon respectively. So this is our generalized result. Hope you have liked the contents in this video, and we hope that this will help you in some way. If you do like this video, and if you do want to see more contents like this, please like and subscribe and share this content with your friends, and peers and colleagues as much as possible. Thank you very much for watching. I'll see you in the next video.